Okay, time is here. Let's get it started. Any questions from last lecture? Someone just asked me right before start very good questions that when we talk about decision making, detection theory last time, we talk about there's a crucial parameter beta. That's the criteria threshold. Either radar operator decide or you decide or your brain decide. The question was whether we as humans has a preference to set up a threshold towards the right more, towards the left more. The answer is it all depends the situation you are in. For example, if you have asked you to do a task, put your finger on the vibrator, and that will produce some amount of mechanical vibration. As I put your finger there, and pull your hand off as soon as you feel vibration. All right, that's standard psychophysics task. You can design now. I can give you this as homework. I said do so, and of course now we can apply the signal detection theory as to how I or through my brain behave like this. Now here's a suggestion. If I tell you that I don't care how many miss, as long as you get it right, and I'll give you $1. And I don't care about false alarm or anything. What should you do? You're going to do this all the time. Right? But if I tell you, I just change my criteria, say, yeah, you still get $1 if you get it right. But I'll take $2 off if you got a false alarm. Then suddenly you're going to have to evaluate how many false alarms. Because every time you pull your hand off when there's no signal there, you get $2 off. Then very quickly you become very conservative, right? This is the exact same situation that I gave you last time. I gave you an example. A radiologist look a X-ray of a patient and decide whether there's a tumor there. Of course, you are making that decision based on same scenario as well. If you as a doctor, I'm completely hypothetical here now, so don't hold me accountable for what I say now. Just give you an example. If you say, well, you know, I think there's a tumor, so I just send a patient to a biopsy, and his or her insurance will pay for this. Me as a doctor has no responsibilities. There's one scenario. So you can lower your threshold pretty low. As soon as you suspect there's a tumor, you send a student off. No student, you send the patient off for next doctor see, get an invasive biopsy. Because you as doctor make a decision now. This could be false alarm, but there's very little consequence to it because he or she, his or her insurance will pay for it, and no one will find your fault. Even the biopsy turned to be negative. However, if a patient has a lawyer who's going to sue you if you get patient done this, but turn out to be nothing, then you will make that judgment very different. So you see, this is the word decision detection theory applied to all scenarios. It depends on the basically we call the penalty or reward that associated with each decision. Now, there are 4 of them. Let me review quickly before we move on. That is, when there is a signal and you decide there's a signal, that's correct. That's a hit. There's a probability associated with that. Or when there's a signal, you say there's decide no signal, that's miss. Miss and hit together is 100%. Then the second scenario is that when there's no signal, you decide there's a signal. That's called a false alarm. Or there's no signal, you decide there's no signal. The correct detection, correct rejection. False alarm and correct rejection together is 100%. There are 4 probabilities there are only 2 independent variables. And we choose to use probability of hit or detection versus the probability of false alarm to plot as a ROC curve. That's the reason. Okay, so today we'll continue with this discussion I started on last Friday. That is how to quantify action potential or spike trends recorded from a neuron. And we said that if you drop an electrode in the brain, you would record a signal like this, with action potential with spikes riding on top of slowly varying waves of the brain. That's like EEG or other growth activities. And then you apply high pass filter and then you apply a small window around each action potential. I expand here, then you got action potential. Because action potential are all or none, only is time matter. I mean, most time people decide peak is time, but you can decide here as well, so long as it's reliable. Let's say we decide peak time is this action potential. That time is denoted here by 1 line. And you can denote this by 1 dot. That's fine. Okay, just for illustration in 1 line. This synchronous time we call the spectrum. A task today for this lecture is how to quantify this. There are 3 ways to quantify this. There are 3 basic ways to quantify this. We're going to go through here. These are very essential concepts that I'd like you to understand. But how do you quantify this? Well, here's the 4 ways. So intuitively, here's what I do. So if I gave you this sequence, say, quantify this. Every action potential sequence or spectrum is a stochastic process. Okay, I just plotted you 1 instances. Now, the first thing to quantify, which I will show you in the terms here, next slides, is we quantify how many action potentials within a unit of time. For example, from here to here, within this time, how many of them? You can convert that to number of spikes, number of action potentials per second. That's called fan rate. The second one, I'll go through that in more detail. I just want to run through. That's the most intuitive thing. I just counted this much time, how many of them. Second one is that I want to know how fast, how often they come at any time. For example, it seems to come closer here, far over here, closer here. That is a pattern, temporal pattern, the pattern over time, because as you see, these action potentials within this time don't come here on an even basis, right? That's the second measure, which I touched upon last Friday. It's called post-stimulus histogram. I'm gonna go over again. And the third one is quantify whether there's a periodicity. You know, this one doesn't quite look like here. Yeah, look at these 2 intervals are the same. If all the intervals are the same, you see there's a periodicity there. That's part of the temporal pattern. The last one is most detailed one, is to see whether I can quantify the interval between this, because it is the interval among all of them that give you all the information. So we're going to walk through in next 45 minutes, all of them one by one. And I'd like you to understand it, and raise your hand if I go too fast. Then I'll summarize it at the end. So these are the 4 situations that we're going to analyze. Mean fan rate, spikes per second, post-stimulus histogram, we call PSTH, period histogram, and interspike interval histogram. 4 situations. I said 3, it's 4. Even though these 2 in the middle is about a temporal pattern. And the last one is essentially contain information of everything, but it's more complex. Okay, the first one is the simplest one. Now, these 4 measures of action potentials is pretty much all you need to read the literature. If you grab literature of neuroscience, since really 50 years ago until now, maybe another 50 years, when scientists quantify how does a neuron respond to sensory stimulus, they use one of these 4 measures. That's why we discuss here. So how do we calculate fan rate? So here's the experimental scenario. Some of the scientists recorded from a visual neuron. Here's a digitized trace from the screen or picture of the screen. And there's a visual neuron. We say the visual neuron has have receiver field that's sensitive to orientation of the bar. So when the bar has this orientation move this way, then you see there's a number more spike here. And orientation was changed. There are a few spikes. This orientation, no spikes. Okay, that's observation. So how did people quantify this? They calculate the fan rate, mean average fan rate within a time interval surrounding it here, and they plot it here. And this is the orientation, and this orientation was called 0, relatively speaking. So that's here. This is the road hertz here. It's the essential spike per second. That's mean fan rate. So this curve shows you this neuron's behavior. This neuron discharging most number of spikes. It is this orientation. When orientation go that way or this way, the fan rate drop eventually becomes 0. Okay, that's simplest quantification of this phenomenon here. Now, how did scientists calculate here? you calculate the formula. Mean firing rate equal to number of spikes within the time window. Of course, you have decided what's the time window. Usually, the time window is the window where you deliver stimulus. It could change. It's up to you. Use it. That's window. Okay. You count the number of spikes within this window, divided the length of time window. Then you get a spike percent. Yes.
And the thing that we're changing the orientation of is a glowing bar.
Yeah, it's bar. So it's like this. If I show if this light is bar. If the neuron, if this orientation I call it 0, then usually, this is more detailed now, we'll talk about it. You haven't moved the bar. If you just leave the bar there, neuron doesn't do anything. But you have moved the bar, but keep the orientation. This is one orientation. This is orthogonal to that orientation, you move this way. But this is the orientation we'll talk about. Is that clear? Yeah.
You measured this in humans?
No, you can, this was done in animal, but you can do the humans. Human responds similar way.
Somewhere in the brain?
Yeah, this is in the primary visual cortex V1. This is a neuron in cats V1. In fact, Dr. Connor will come give a lecture a couple of weeks about visual system. You'll hear a lot of them. I just pull out as an example. Now, this can be something else too, but in this case, is a neuron in primary visual cortex V1 of cats from this study. Okay, got a question? Okay, so that's the formula, pretty straightforward. Now, of course, I said it like last time, is that when scientists do this experiment, and the action potential here are random, so they just don't do once. They usually repeat many times, like here, once, twice, 50 times or 100 times. So when we calculate firing rate, mean firing rate, you have to take into account of that. If there are n times, you did n times, or called n trials, the mean firing rate would be number of spikes within time window from n trials divided by the length of time window and multiplied by number of trials. So mean firing rate, it means spikes per second, that's unit. Okay, this is how you calculate. So I can give you a scenario like this, but with a different situation, you should be able to calculate. That's the first one. This is the simplest one. Now second one, if we move along here, is this example I used last time. This is the auditory neuron in frog auditory nerve. Responds to 500 milliseconds of tone. And here, each dot represents action potential. So there's one trial. So this was repeated 50 times. Now, this pattern we also refer to have a name called dot raster. Okay, dot raster, each of my action potential. Now, of course, if I give you this to, I say, calculate the mean firing rate, you just apply the formula I showed in last slide. You can calculate mean firing rate. But mean firing rate, as you can tell, if I calculate that, I just count the number of spikes between 0 to 500 milliseconds. I count how many of these, count all of them. Divided by 500 milliseconds, divided by 50 trials, I get a mean firing rate. But that number, one number, doesn't tell you an important property here. That's you can see there are more spikes here, fewer spikes here. Right? There's a pattern over time. That is called diabitation. And such pattern is very important. So how to quantify that pattern? Mean firing rate is inadequate. So this is a measure we use called a post-stimulus histogram. The way this is made is very much like mean firing rate, except now that time window is no longer entire stimulus. I choose time window. This is arbitrary. Okay, how we choose it, we'll see next slides. Let's see, there are 100 milliseconds here. I divided with 10 beans. I choose 10 beans, 10 milliseconds as time window. 0 to 10, 10 to 20, 20, 30, 30, 40, so far, so on. Then within that 10 millisecond time window, I use the same formula I used in last slides, calculate mean firing rate. Then you calculate mean firing rate for that 10 millisecond being, that is plot here. Then you go on to plot all of them. Then you get a plot like this. Now you can see intuitively, this reflects a pattern here now. That is a neuron, this neuron did not fire until about almost 20 milliseconds, 2 beans after beginning. That is delay, because neuron never fire until sometime after the stimulus is perceived. And then fire a lot more, almost about 260 spikes per second at the third being. And then number of neuron firing rate goes down as it move on, eventually close to baseline. Yes?
What exactly is the y-axis of the dot roster representing?
Here, y-axis here only indicated the number, the sequential number of a child. So I do once, I call it 1, go twice. So the order of this is, in this case, is meaningless. You can reshuffle it. It's simply, in this case, it's a sequence, it's an actual sequential order. When I play once, I got a spike plotted here, twice, 3 times. So it's a sequential number. Good question. Yeah, it has no other meaning. Just saw the layout, you can see it. Okay. So this pattern is called post-stimulus histogram. This is one of the most used, analyzed in the literature. So I like to understand and be able to analyze. For example, if I give you homework or exam questions, I give you a whole bunch of numbers like this. Then I say calculate histogram. You should be able to do this by hand. It's very quick, so long you understand the concept. Okay? And of course, you are given a lot of numbers, then you can use your MATLAB to do it. That's easy. But conceptually, you can do it by hand. Yes?
So the y-axis, it says spikes per second.
Yes, spike per second, yes.
Wouldn't it be just the number of spikes per the amount of the bin time?
Yeah, well, right. So you first count how many number within this bin, but then divide by bin width, then normalize by spike per second. So this way, no matter what bin width you choose, you can always end up a spike per second. Yes?
So if you were looking at like a given time period, you would count the number of dots and then divide by the time period, and then you would divide by
number of
trials.
Correct.
So like this case would be 50.
Yes. Okay. So this way you normalize by number of trials because somebody can do this 100 times, or you can choose a subset of this. So what you get here is spike per second is a unit. It's just like physics. Every variable has unit, right? This is unit for the mean fan rate. It doesn't depend on the window length you choose. It doesn't depend how many trials because both of them are normalized. Okay, this is second measure. Now, of course, you can see, you already have a question, why did I choose 10 milliseconds? That's arbitrary. The way you choose the window width and it has something to do how accurately you can capture this trend. For example, I'll give you an example here. Here's a spike trend. We choose a window width 100 milliseconds. We calculate histogram, and you got this pattern. Okay. Now, if you choose the window width too big, you won't capture the pattern. Of course, the fan rate is extremely, the window width is the whole thing. Now, but if you choose window width like this, sometimes you can, smooth this window, you can so far so on. But the point here is that you can see from this analysis, here is a smooth sliding window. So when we calculate histogram, we don't overlap a window, just one window after another. But this show you the width of a window really determines how accurate you can calculate the temporal pattern here. That is not so obvious to eye, and that just demonstrates that point. Now, the third way to quantify this is for the situation, the action potential are periodic or have a periodic component or part of the action potential are periodic. For example, I now plot the experiment from an auditory system. This is the action potential, actually real action potential recorded from a cat auditory nerve by 2 professors in this department, Mercedes Young. It was 40 years ago, before all of you were born. And both of them have retired now. Years ago, they used to teach this class. So I pull out one slide from the work they published in the 70s. So here's the experiment. This is tone beep, boo, right? Give a boo. You all know tone is a sinusoidal waveform. So if I expand this tone, it's like this. A tone happened to be 768 hertz. The period is 1 over that is 1.3 millisecond. So when they play this tone, they got action potential at enlarge here. See, these are the action potentials. Okay? So now what I want to do is we want to calculate whether these action potentials capture the periodic pattern of this. Now, if I give you this action potential, you cannot tell. Maybe here, but I'm not sure here. So the way to calculate it is the following. To quantify whether an action potential sequence or spectrum has a periodicity here is the following. So here's a signal. It's periodic. I will take multiple number of cycles from 1, 2, 3, 4, 5, 6. It takes 6 period. That's arbitrary. You need to take at least 2. If you take 1, you cannot say it's repeat. So you at least need to take 2 periods. Usually you take multiple of them so you can see it. So arbitrarily, we take 6 periods here. So we chunk this data corresponding to this 6 period. From here, that's chunk data here. Then next 6 period, a chunk here, I put here. The third one here, so far so on. Okay, first one. Second idea is, of course, we just said earlier that action potential is all along. So I can replace each of the action potential by a dot, indicates time. Okay, and that here, this here, this here. Now, of course, I can get it to a point that I convert all of the data first, do the same thing. I just want illustration. So once you have this, and if you can continue, this is very long, you can get many trials. That's essentially is this data raster we're talking about now, right? Then you would apply the same calculation you apply to post-student's histogram, then you get this histogram. This axis now is this time, 6 period. Y-axis is the same thing for the period histogram, except the histogram period is very narrow now. I did not plot here. You can barely see that. It's a very small window. Okay. Once you calculate that, and you get this histogram, we call it period histogram. The only difference between this period histogram and the post-stimulus histogram is that this time, from 0 to end of here, equivalent to a multiple time period of a signal, because signal is periodic. Okay. You can only apply this to periodic signal. Okay. Now, you could apply this whole thing using these methods, get a period histogram, get a post-stimulus histogram, get this, except you will not be able to say periodicity. So period histogram essentially is the same thing like this, except a much shorter and much finer scale. Why we do this? Once you've done this, you can see this response here now has this 6 period. And the distance between the 2 peaks, 1.3 milliseconds, that's exactly what's in the stimulus. So by this data, scientists can say now, this outer nerve, when it responds to pure tone, have this property we call it's phase locking. It just follows the time period of phase locking. That's the first step. But this is not a quantification yet, because how accurate is the follow? This is a very clear case. It could be much murky than this. How you quantify this? So we take one step further to quantify this, how much phase locking is here. Then, before I go that, I give you another example. That's from my sensory system. This example I gave you last time. Say if you touch your skin, there's an action potential coming out of the fibers here, nerves that innervate your skin surface. The detail of this we'll discuss later when I come back to talk about my sensory system. But point here is that if I touch your skin, this indentation, touch your skin, then I begin to vibrate on your skin tip. Then action potentials I record from your wrist here would have fine rate like this. Okay. And you can plot the histogram like this. Now, I have not touched upon the interval here. Let me save this, I'll come back later. This is the last one, interspec interval histogram. I'm going to tell you about. But what you can see here is that there's period here. Okay. So you can use the method, just talk about last slides, to quantify period histogram, being able to tell what is the period here is. Okay. In this case, that. But in this calculation, they only took 1 period. The stimulus has a period of 100 milliseconds. So this is why I just told you, if I just give you 1 period, you cannot tell it's periodic. If I do 200 milliseconds, you will see another peak here. Okay. 1 period in theory is the same thing as a 10 period, but 1 period you cannot tell. There's a repetition. The last one here, we did this for 6 period. Okay. Now, how do we quantify this? How do we quantify there is a periodicity in there? So when there's a periodicity, that is when sinusoid goes from 0 phase and back to 360, it goes through a circle. This is circular. This is some similar thing. You might have seen this in physics lectures. When sinusoid goes phase from 0 to 180 to 360, it's like you go around the circle. Okay, and there turns out there are 2 ways you can quantify it. I'll just give you a formula here, and I'll find a chance for you to exercise this in your homework. So to quantify how much phase locking in a spectrum, you can use these two methods. One of them is called, you calculate vector strength using this formula. This is essentially based on this notion that if this goes like this in circular statistics, you can compute how the amount of phase locking use this. In this case, T of I is the time of spike. So every dot of spike is T of I. T is the period of stimulus. Vector strength is vector strength. You calculate here. You can do this by hand. But these days, MATLAB computer speed are cheap. MATLAB is everywhere. So you can also use second methods. Compute something called the synchronization index. That is to take spectrums as time variables. You compute its power spectrum. And then you then find out the power spectrum corresponding to the component of power spectrum. It is a periodicity frequency. That divided the component, it is 0. That gives synchronization index. Both of them are equivalent. And this one you can do by computer. The reason that one is still useful, this is directly calculate the vector strength corresponding to the period here. Whereas this one, in order to calculate the here, you basically calculate everything, but you only use that F0 point. It's more expensive computation, but you can do this. And I'll give you an example in homework for you to exercise this. So what is this good for? Okay. Once you calculate this, for example, you calculate here, then if you go back to the question, if I calculate here, this gives you a number. Okay. Now, it turns out for auditory nerve, when you have a frequency is very low, lower than 1,000 hertz, here is 6768, you can see this pattern very clearly. As the sinusoidal frequency become higher and higher, this pattern become less and less clear, eventually disappear. And I'll save that to the lectures when I come back to talk about the auditory system. Then we'll talk about what this number mean across different frequencies. Yes?
So, at least for like low frequencies, is it true that like, because I saw like 1.3 milliseconds,
yeah.
that if you like average it, it's equal to the actual frequency of the sinusoidal wave that you're listening to?
Yes, it is. So 1.3 millisecond is equivalent to this frequency.
And the frequency that your things vibrate with average?
That's right. So this is the exact frequency your ear will vibrate, and that you hear. Yes?
How would you, by only measuring the spike train, would you be able to backtrack and figure out whether or not the animal was listening to periodic?
Yes, you can. You can. That's actually a reason analysis. So if I don't tell you anything about a stimulus, for example, if you give spectrum, you calculate this. So you could tell from here what is the frequency the animal was hearing.
But how would you choose the period that you calculate that for you?
That's a good question. If you don't know anything about a period, what you do? Well, you do autocorrelation. It's from signal processing. Then you do spectrum. So where is the peak?
Okay.
Yeah, if there's a period at F0, the spectrum is flat most time, except F0, boom, there's a peak that come out. Okay, so that's how you figure out. That in fact, this is how engineers, without knowing a frequency component of a signal given to you, you just do spectral analysis, say where's the peak. You could have more than one peak. But in this case, you will have a very large peak corresponding to this frequency. Yeah, you will see this when you analyze, maybe this Friday's homework I'll give you to do this. Very good question. So it'd be better if you know the frequency, you just go for that component directly. If you don't know, you look at spectrum, it'd be very obvious. Good question. Any other questions? So we'll talk about what does it mean biologically when it comes in. It turns out this pattern called phase locking is crucial for us to hear music. It's crucial for us to tell sound come from left and right. This is the function auditory system use, because this can precisely track 1.3 millisecond. This is very, very tiny time. So that means the nerves in auditory nerve can track that. Now, this is not something, you do not see this in visual system. In fact, our eyes cannot track things happening this fast, nor do you see this in here. A vibration, if I vibrate here at about 768 hertz, you could not backtrack this because the nervous system doesn't carry that information. That's why we analyze But I'll save the meaning later on. For now, I'd like you to understand how to quantify this. So let me now go back to the second example I was giving you for somatosensory system. If I vibrate your skin periodically with a vibration frequency about 10 hertz or 100 milliseconds, and if I calculate period histogram, I would get something like this, except I only plot one period here. Okay, and if I plot another period, you will see this peak here. Okay, now, but another way to look here, now we're talking about the last measure we measure, is if you, as you can see here, if the neurons discharge periodically at 10 hertz, then I will be able to tell from the interval between two, right? I don't have to calculate the whole thing as FFT. Then one way you can do this is just calculate the intervals between two spikes. If you have this much spike, I calculate interval between every other spike, two spikes. If you calculate that interval, you plot histogram, you get this. This is called inter-spike interval histogram. This is a little bit tricky. Let me walk you twice through here. That means if you have n spikes, okay, let me go back here. Go back at these plots and look here. This is the last one, but it takes a little bit extra time. So, for example, this is the first spike. This is first, second, third, fourth, nth. Right? If you have n spike, you would have an n minus 1 interval. If this is T1, T2, the interval, first interval, if you call it tau, tau 1 equals T2 minus T1, tau 2 equals T3 minus T2, so on. That's interval. So you have a bunch of interval. You have n minus 1 interval. Then you can make histogram of this. Okay, that histogram for this case is here. Is here. Then this histogram show you there's a peak about 100 milliseconds. That means there are a lot of intervals here. It's about 100 milliseconds. But why there's a bunch of things here? Why there are a bunch of things? Why we just don't see this alone? Why we have a whole bunch of intervals that's just 1, 2, 3, 4 milliseconds? Why is that? Anyone have a guess? Why we have an interval here? This is real data. And then, yes. Yes?
Possible short-term memory?
Could be. But the short term is the key. You hit it right. That is, when spike come, even though there's periodicity, it don't just come one every 100 milliseconds. Sometimes it have 2, 3 together. About 100 milliseconds later, another 2, 3, 3, 4. Okay. So the short interval is about this coming in clusters. That's where you can almost say here. Okay. Those intervals map here. But the dominant interval here, long intervals, is here. Okay. So essentially, if you can calculate, quantify interval, you calculate everything. If you can get interval histogram of this, we can backtrack to calculate period histogram. I can calculate finally, calculate everything. So our major goal today in this lecture, key concept, is to understand how to compute interval histogram, how to model this, how to simulate this. Okay, now the next 20 minutes is a real important thing. The final entire thing is very simple, straightforward. How do we do this? So let me walk you back now to the mathematics. This is key of today's lecture. So let's go back how we formulate this. So if the spectrum is like here, this is a spectrum. By the way, I just realized that today when I review my lecture, because I use the new PowerPoint, I think in your handout, this tau was distorted, right? Did anyone look your handout? Can you see the tau? Yeah, that's because my computer now has a new PowerPoint. I didn't pay attention until I was review. But anyway, I will correct the handout and ask Tia to repost it. But just for now, just take notes here. Is all the Greek letters were distorted in the newer version. So I dig out the older version here. Okay, so that's each one is a spike. Okay, the spike time, interval called tau. Now, some of you might have learned this from probability. How many of you have seen the Poisson process in probability class? How many of you? Okay, thank you. Some of you have seen. So this is a process. It's called a point process. But mathematically, you can plot the equivalent plot like here. Okay, so here, where y-axis is the number of count. Since we consider spike, it's number of spike at each time. So from 0 to here, there is no spike, so it's count to 0. At this time, we call it W1. Spike number suddenly increases to 1, and until W2, until W3, 4, and so forth, so on. Okay, so mathematically, this presentation, spike count, the n at the time t, how many spike count here, is identical to this. The both are interchangeable. So mathematically, if you have taken a probability course, you might have remember here a Poisson process, a Poisson distribution rather, of p of n of t equals to small n. That means within the time period of capital T, there are n spikes. This is equivalent to this probability. These lambda were distorted in your handout, but this is what it is. Okay. Now, what about this one? And this turned out it's easier to work with. So now we give you distribution of tau. We don't talk about count now, tau. And this tau, this distribution tau, turned out to be is exponential distribution. That is the probability density function of tau equals to lambda multiplied by exponential of minus lambda tau. This all of them distorted, if you can take a note here. Okay. Now, so either way can work, but turns out for scientists to analyze spike, it's much easier to work in this fashion. So we're going to stick with this fashion now, but mathematically you can prove either way is the same. So what does that mean? That means if you have spike trend like this, if this is a Poisson process, then its interval distribution can be precisely described by this exponential distribution. So what is a Poisson process? Here's a Poisson process. Let's just give you a definition, whether you have taken course or not. That is, time you have events here, events is only one at a time. You never have two events together. Okay, so at any time interval smaller enough, you have one event. Therefore, when you look at a count, the count always jump to 1. Okay, never 2. This first one. Second one is that anything happen here, between here and here, between any time interval, this line has no memory of the past. So if I look at time here and time here, they're same. No, I'm sorry. Time here has nothing to do with what happened here. You can go look here, has nothing to do with the past. There's no memory. Third thing is that if you look at a time here, during this period, they're same. There's a stationary. So 3 properties. I'm not going to ask you to memorize this, or just tell you what defines Poisson process. Then we'll talk about what's interesting is why the real neurons don't act as a Poisson process. We want to start a Poisson process. This is the simplest, most beautiful mathematical formula we can come up with point process is the exponential distribution. But real neurons don't like this. But we start with this simple thing like this. Then we see, in order to model real neuron, how to break down each of those points. It turns out among 3 properties of a Poisson process, the first one is beautifully satisfied by neuron, because neuron always give 1 spike, never give 2, okay? Because of all along property. So first property of a Poisson process that having 1 point at a time is automatically satisfied by neurons. The second property, that is what is happening here, has nothing to do with the past. There is no memory. It doesn't quite often, because pretty much in nervous system, everything happening now has something to do, at least for the recent past. Best example is the one that you're going to exercise on when we do SBE II Lecture together. It's called the refractory period, right? So you know when we have 1 spike, at a short time period after this, you just kind of have another spike. That's called absolute time period. So that is memory. Okay, Poisson process does not deal with this. And we'll see next slide how to modify this. The third thing is the stationarity. Poisson process says that if you analyze here, or a month later, a year later, everything's the same. Well, that's not quite the same. When we wake up this morning, your mind behaves very different at the end of the day after taking 4 or 5 classes. Okay, but in neuroscience, most time we analyze the neurons within a short time period. So assume it's stationary. That's how we go now. Okay, so this is the formula we come on. Now, if I gave you a action potential trend like this, as a calculated histogram of tau, what does it look like? Since we know if this is a Poisson process, it's exponential and It's just like this. This is a histogram of interspike interval. If it were Poisson process, it's exponential. Does it make sense for real neuron? Can we use it for model real neuron? Can we? Can we use the model real neuron? No. Why is that? Which one? Which part of this doesn't look right? Yeah. What? Yeah. Very good. So because of refractory period, we cannot have this. This part means the two spikes can come in definitely close. That cannot be happen. Okay. Then how to modify this? Well, in order to modify this, we can modify this interval histogram like this one. For example, we change the curve to something like this. It's called gamma distribution. It's non-Poisson now. We allow the initial part has no value, then gradually increase value. This is almost a mirror, reverse image of refractory period. So we can take care of that. Okay. So now it turns out that if you want to model real spectrum, you want to use something here. I plot 5 examples of a gamma distribution. This is a gamma distribution. It's less analytically workable than Poisson, but this is. Okay. So how does a real neuron look like? If I give you 1,000 spike, actually you can calculate 999 interspike interval. You calculate histogram. Here's what you get. Okay. So here is the interspike interval histogram of a real neuron. You calculate like this. This part is exactly because of refractory period. Okay. And this neuron apparently has no periodicity because we don't see another peak somewhere here. All spikes coming fairly close. So most spikes are coming about 10, 15 milliseconds to each other here. Okay. So that's the one. Now, here's the question. Now, why I want to go through here? Let me tell you what is coming. So here's the concept we want you to learn as biomedical engineer. So if you do biology experiment, if I give you a neuron, let's say I give you a neuron, I say this is ultra neuron, study what's its property. Then you play a song to an animal, human. Let's say animal, this is how we get a neuron. You play a song to this neuron, to animal, you record from neuron, you quantify this, you analyze. Fire rate, post-stimulus histogram, period histogram, you say, I'm done. So for biologists, this is most worthy, done. They stop. They quantify their published paper, we move on to start next neuron. But there's one more step you can do as an engineer and a computational scientist that's useful. That is, once I can quantify, since I have action potential trends, that's a stochastic process. Then I can compute a mathematical model of this. Once I have a mathematical model of this, I no longer need this neuron. In any time down the future, you want me to study neuron or ask questions about the neuron, I use my model to regenerate a spike from here. This is what I'm going to take you through here. From quantification to modeling to simulation. Okay. And this is very useful because, give you an example, some of you must have read the brain-machine interface, right? It's people lose a limb, okay? And they put an artificial limb here. I want the limb to move. I want to use my finger like this. But how do I control this? Well, you know, in normal person, when I say I want to do my hand this way or that way, there's action potential trend come here. Okay. So in theory, you can figure out action potential trend, program in the computer chip, then you put the artificial limb here. You can use that spectrum regenerated by your model to move a finger exactly the same way a normal human would do. This is a simple example. There are many, many examples. So how do we do that? How do we take this spectrum, model this similarly here? Okay. We use spike interval histogrammatic example. If I give you a real spectrum, the step one is to calculate ISI distribution like this. Step two is model this. Model this means using a formula. And we said just in last slides, this is very much like a gamma distribution. Now we use this gamma distribution to feed the data. So now we have this gamma distribution. The last step is take the distribution now. In the probability course, you must have learned this if you remember. That is for any random variable. If you know its distribution function, or if it's continuous variable and know its density function, then we can regenerate the random variable indefinitely, right? So this function essentially is the probability density function of tau. Once you have this function, you can regenerate the whole spectrum again and again that satisfies this interval. And that's what I want to do here. So let me skip this one now. So how do we generate the intervals here? So this distribution here is the gamma distribution. How to generate this interval here? The way to synthesize any regenerated any random variable is begin from uniform distribution. Okay, it's the formula set here. That how to simulate Poisson process. Let's talk about first how to simulate Poisson process, then go back to our gamma distribution. Gamma distribution is more difficult. So, of course, in MATLAB, you can go there. There's a function called a Poisson process. You type in, you have everything. That's cheating. Okay, you can't do that. So the way to generate a random variable, this is very useful information, is that you start from a simplest random variable. You have to start from some random variable. Okay, let's call it U. U is the uniform distribution between 0 and 1. Right? Distribution function is flat between 0 and 1. And if capital F of t is a probability distribution function of random variable tau, then W as inverse of f of u is random variable with probability distribution function. Okay. Is that good? Just take some time to digest this. This is a mathematical theorem. So what happens is following. Here's what happened to the Poisson process. Because the Poisson process density function exponential is a distribution function. You can do the integration. It's here. This is distribution function. Everyone understand the difference between density function and distribution function, right? Good. So this is a distribution function, probability distribution function of Poisson process. This inverse is that. So what does it mean? Funny. If I allow you in MATLAB to generate a random variable that has uniform distribution, every time we generate a random variable with uniform distribution, you plug it here, then the calculator here, that variable is exponential distribution, tau. So that means if I ask you to generate Poisson process spectrum that is exactly the Poisson process, here's what I do. You produce one of u, assuming you spike start from 0, and you produce u, plug into here, calculate w. W1 is your first interval. So first spike is at w1. Then you do the second time, produce another random variable u2, and you plug here, you got a w2. The second spike time is w1 plus w2. That's second spike number. So first one. You can generate as many intervals you wish until you produce the spike you want. Now, this is for the Poisson process. But real spectrum are not a Poisson process. It's this one. Then how do we do this? Then if I give you distribution function spectrum interval like this, you got this distribution. Then you have to integrate that to get your distribution function. If you cannot do it mathematically, you do it numerically. Then you apply this formula here. Get this? Okay. Is that clear? It's a lot of puzzling on your faces. So I'll let T8 walk you through it. Okay. So idea here is to calculate this and inverse of this. Someone raise hand there. Yes.
How did you get 1 minus here?
1 minus what?
How did you get that formula?
Oh, how do you get it? One?
Just why?
This one. Oh, this is inverse function. So f minus 1 means inverse. So
Oh, no, just the original function.
Original ft. Okay. So if it's not Poisson original ft, you got it from an integration of a density function. So original ft, this one, this is distribution function of random variable tau. Okay. So maybe I can. Let me can. I have a couple minutes, and let me finish this. And I think the rest of me is pretty clear. Okay, so let me use a blackboard to finish the last part. And I like you to, all of you to. Okay, so the microphone stop now. So I'll yield very loudly because as soon as I exit here, I'm stop here. So this is a very important concept. I'd like you all to understand. So suppose I'll just walk you through what I just went through. Suppose I give you a whole bunch of spectrum, a real spectrum. I say, make a model of this and simulate the spectrum and statistically, not the same. So you start with spectrum and you have many spikes. And you calculate tau 1, tau 2, 3, all the way to tau n. Right? You can calculate this numerically. Then from here, you can calculate the histogram of tau. Probability the histogram of that is density function. And that, use all of that, you can calculate something like this. Like this. Now, if you find a nice function to fit it, you can fit this. But the next thing, if you don't fit it, that's okay. You do everything numerically. So next thing is calculate a density function, capital P of tau. A density function is integration of this, right? So that'll be a function like this. And this is F tau I talk about in my slides, capital F tau. Because the density function, probability distribution function, mathematically, you know it's monotonic. It has to be monotonic. Because it's monotonic, you can do its inverse function. Okay, so this value, if I call this S here, this is let me use F here. So then this value here will be F minus 1 S. Right, that's what I mean inverse. So if you cannot do it analytically, you just do numerically, you get this function. You can do the inverse. Once you can do inverse, you plug that formula, give it to you. You will be able to synthesize. So idea is the following. I give you a bunch of real spectrums. I say simulate this. Then you go through this process, then you can generate another spectrum. Of course, it's not point-to-point identical, but it's statistically identical. You can generate 1, 10 of them, 100 of them, 1,000 of them, as many as you wish. Then if you do so, using a formula, that spectrum is statistically identical to the one you begin with. That's the whole idea. Okay, is that clear? Okay, so then my slides, my PPT, the rest of the couple of them, that's not so important. This is the most crucial concept. Spend some time on this. I'll make up homework for you to exercise this. If I have more questions, discuss with TA. Okay, thank you.